thank you everyone for being here for this webinar where we're going to make the state of the art of Hiphen, so where we are at least on 3D sensors technology applied for plants in 2022 and how we use it. Maybe for a start, I'm here today with Jeremy. Hello, Jeremy.
Hello, everyone. Happy to be with you today. So maybe I will start by presenting myself. So Jeremy Labrosse. I'm here at Hiphen for 6 or 7 years now, and I am an agronomist, but with a specialization in new technologies and sensors in general. And at Hiphen now, I'm leader of the research and development team that is always looking for new sensors, new algorithms, and we are trying to give you the best products at the end.
Then myself, so I'm the CEO and founder of Hiphen. I have a PhD degree in plant phenotyping, and I'm really happy to be here with you today as we try to do one webinar every month. So a very short introduction of Hiphen in one slide. So Hiphen is a company specialized in plant measurement, so plant phenotyping. We work across a broad area of markets that comes from breeding markets to crop product evaluation markets, to vertical farming markets, and also all what is agro-processing markets. And we're able to measure plants from satellites, drones, embedded sensors in tractors, what we call phenostations, so it's fixed areas and smartphones. And there's always the same types of algorithm where we try to use as much mechanistic knowledge as possible. So how does the plant work? We're agronomists first, but also to make the process to use cloud-based type of IT infrastructure and intelligence infrastructure in order to go into your workflow in the most seamless way. And this is really our main motivation. So let's get a deep dive into it now that we're there. So let me first introduce you all this 3D context on which we sit in the world of phenotyping, so of measuring plants. So what we love to say at Hiphen and I as well is that there's 6 dimensions in plant phenotyping. So if you want to measure plants with sensors, you need to take into account 6 dimensions. The first dimension is a kind of data point or a vector of points. That's what we call the X. Then you have a Y that is making you an image. The Z, that is the depth, so it's making you a 3D images. But you also have 3 other dimensions that are really, really important. The first one is at which wavebands, where in the electromagnetic spectrum are you measuring your data? Is it in the visible? Is it in the thermal, infrared, thermal, etc.? Is it more in the radar space? The direction of your sensor, and there we will see some illustration here that the direction of your sensor is really important. And regarding plants, and mainly regarding plant, time is critical as you can have some changes that occurs extremely rapidly in plants as well as long term. This is not covered by today's webinar. We're really going to focus on the 3 first dimension, but please be aware that you always need to think with the 6 dimensions before being able to make any systems that are able to record anything. Then, also to introduce things, when we speak about 3D data point, we can speak at the canopy level. So we work a lot at the canopy level to estimate biovolume, biomass, height, etc. We can speak at the plant level, so how to characterize the architecture of a plant in general, and at the organ level, so how to quantify the size, the volume, the shape of an organ within a plant, within a canopy. So really, those different examples we'll give you, we try to be at those 3 levels and to give you some concrete examples there. Last thing to finish my introduction is mainly what are the types of traits we're looking at when we use 3D? Well, it's mainly architecture indicators, so how is my plant? What is the architecture of my plant? The easiest is plant height. Of course, then we can think also on some kind of problems like plant lodging. Plant biovolume, plant and canopy biovolume, which is I guess, the first proxy of biomass, plot length, true crown surface, leaf angle, the quantity of light intercepted by the canopy, which we call FIPAR, fraction of intercepted photosynthetically active radiation. Leafer index, thus, so leafer index is the amount of the surface of leaves you are having within a canopy or a plant. And of course, I already mentioned it before, organ size. So those are really the kind of core things we're going to want to extract from 3D data points. We're going to see as well that 3D data points allows you to be more accurate in more complex use cases, such as wheat ear counting. So it's about a density of wheat ear, but it could also work with a density of plants. So let's get on with it and let's look with Jeremy what are the different technologies available on the market so far.
So yeah, if you want to have a 3D measurements of our plants or of our vineyard or whatever you want, you will have to have sensors. And from our own bibliography to in the phenotyping world, we identified the 4 main families of sensors. So we have the LiDAR, the laser 3D scanner, the time of flight camera, and the stereo vision or structure from motion technology. So basically, depending of your use cases and depending of the accuracy that you want and the kind of traits you want to compute, we will help you to choose the good technology. So how we can discriminate those four technologies? First, it's the footprints of your sensor. So depending of the technology, you are able to have a more wide or narrow view of your scene. So depending of the integration constraints that you have in your use case, it could be important. Then you have the distance between your camera and your plants. So, for example, the LiDAR is really hard to work with in a really constrained structure, like vertical farming, for example. But time of flights are really the way to go because they're able to work in a close range. Then you have the resolution of this technology and how it will describe your objects. So some of these technologies will just describe the outside part of your objects, and others are able to penetrate within your objects to describe your plant in more details. And the last thing is, do my plants need to move, or my sensors to move to have a 3D informations, or is it working with nothing moving? So we will go into details now for each sensors and for each technologies, and present the pros and the cons. So the LiDAR, so it's one of the ones that we are using a lot at Hiphen, is really the way to go when you are working in field conditions outdoor. So you can be bothered by the sunlight, but that's not the case for the LiDAR. So you are able to have 3D conditions in your field, 3D informations directly in your field. It's really accurate. So it's sensors that are now well industrialized, especially for the autonomous car. So it's really accurate, and it can work in outdoor conditions. And then we have the time of flight camera. So sorry, for the LiDAR, with the one that we are using a lot at Hiphen, it's just a scanner that work on one line. So you need to move the sensors or to move your plants to scan your objects and to have for this example here, we have a canopy of width. So to describe this canopy, we moved the sensors along the whole canopy to describe line by line the canopy and to have a full 3D reconstruction of your canopy. Then we have the time-of-flight camera. So the time-of-flight camera works in a really different way, and it will, in a glimpse, just take one image of your scene. So you don't need to move your object or your sensor. In one image, you have a 3D reconstruction of your scene. It's one of the, so it's quite new, but now it's one of the cheapest solution on the markets. But the resolution often with those camera are really low compared to the LiDAR, for example. But still, with this camera, we are able to have, for example, here we have example with sweet potatoes or broccoli, and you can see that we are able to see quite a lot of details. And the great advantage compared to LiDAR is for a LiDAR, you are between your LiDAR and 60 centimeters, you are blind. You are not able to compute 3D informations. And this blind area with the time-of-flight camera is around 20 centimeters. So if you are doing, for example, vertical farming or in greenhouses where the space is really a constraint to put your sensors, time-of-flight camera is really the way to go. Then, so we have the 3D line scanner. It's quite a difference. It works with the projection of one line. So you will see one laser in your objects, and you will have, so you have your line, and you have another sensor looking at this line and looking at the deformation of the line, and the deformation of the line is linked with the height of your objects. And by looking at this deformation, the system is able to retrieve the 3D information. So at the beginning, those sensors that are quite expensive has been developed to measure the quality of electronical boards in plants. So you will have a lot of details. So for example, here we have just a leaf of a salad, and you can see all the details really accurate. And for us, it's really the most precise technology on the market now. But as it has been designed for electronical components, it's the field of view is quite narrow. And as you need to move your objects, the throughput of this method is quite low. So it could be used in really specific area, for example, to measure, to phenotype seeds, for example, on a conveyor belt, but it has a constraint.
And a lot of occlusions.
Yeah, and you have, as you have your line, the source of your line scanner in one part of the system, and another sensor in the other part to look at the line. If you are not able, for example, to describe with a wheat canopy, because there is a lot of occlusions that this technology just cannot manage. And then, so the last one, the stereo vision or structure from motion based on RGB camera. So it's usually what we are doing right now with our eyes. So we are seeing with our own RGB camera, our eyes, one object from two different point of view. And by matching those two images, we are able to compute what we call disparity map. But at the end, we are able to compute a depth map. So either you do this by stereo vision, so with two camera, or it's what we can use it in a different way. For example, when you have RGB camera mounted on a UAV, you have just one camera, but the camera is moving, and you will see your plants from a different point of view. And you will use the same kind of technology. In this case, we call this structure from motion to retrieve a distance and then to have a 3D reconstruction of your scene. So the great advantage of the technologies, it's based on the RGB camera. So you will retrieve for each point the RGB information. So for example, you can use the 3D information to have a segmentation of your objects, and then per object have a qualification of your objects with the colors. The problem with these sensors are to match the match of the two images is not always perfect, so it could fail. So that's why, for example, here you have a third sensors, and this third sensors is just a light. So you will project a pattern, a light pattern on your objects to help the match of the two image. So that's it for the four main technologies. And now I will just go into little more details because depending on the technology, you will retrieve different kind of data. So for the LiDAR, you will have really a full point cloud with so here the example is a plot of width, so it's a canopy of width, and with the LiDAR, the LiDAR is able to really go within your canopy and not just describe the contour of your canopy. So you are able to describe, for example, the density of matter in your canopy. And for example, if you are looking at traits related to light interception, not just at the base, not just at the top of your canopy, but the global light interception of your canopy, LiDAR is really the way to go. With other technologies, so stereo vision, time of flight, and 3D line scanner, we can debate, but at the end, you mainly have just the contour of your objects. So you are able to compute the height, the biovolume, for the case of microplots of width in your breeding trail, for example, you are able to compute the exact area of your plots, but you cannot see so within the canopy. So depending if you are using LiDAR or other technologies, that's a constraint that you need to keep in mind.
So the debate, because people can agree or disagree with that, the debate is about resolution and occlusion. More you have occlusion and more you have a depth map of the contour, less you have occlusion, less you have this depth map. Same thing goes with resolution. So there's no real depth map versus 3D dense point cloud. We agree with that. It's just a kind of way to visualize a little bit what would be the suited technology for you. If you want to go deep into the canopy, today in 2022, we highly advise LiDARs. If you want more to understand the shape of a single plant, or if you're having less resolution / occlusion issues, which happens a lot for plant scientists, then the other technologies can be really, really interesting. And that's the example I'm going to try to show right now. So I'm going to show you some kind of simple examples we're doing mainly actually with non-LiDAR things. So the first one is what we're doing with the phenostation for vertical farming. So the first thing they want is fresh biomass. And fresh biomass, okay, might be changing to estimate through sensors, but at least we can have biovolume that is probably the first proxy for that. And for that, well, you can create a raw data point using the example time of flight camera. So here we use the Visionary T Mini from SICK, but there's others from Modos, etc. The main thing you want to do when you're doing that is to be able to retrieve the soil. Whether you're in vertical farming, whether you're in other situations like for breeding companies in breeding trials, you always want to get the soil and to be able to have the soil as the baseline. So that's what we're doing then. We're finding the soil as the baseline. In this case, it's very simple. We'll see some cases where it's more challenging. And there we're having the kind of this depth map with the soil at zero level. We can extract the height. So the height is very easy. It's the highest point of your data points on your metric height computation. And we can also compute the biovolume. So the definition we use of biovolume is to say it's the F cover, so it's the green fraction times the height of each pixel in inverse. So it's a kind of integration between in millimeter square of the F cover and in millimeter of the height. And that gives you a biovolume that is extremely accurate. So we make a lot of validation using tubes, by example, and looking at if we're able to estimate the right volume of those tubes. Same thing, different technology. So we can do that also in breeding trials. So here you're having a breeding trail, I think it's 15,000 plants individual of grass, but we could even imagine we're also doing that on strawberries or on lettuce or on any type of plants that can be individual. I think we've done that also on sunflowers at early stage. There, the idea is to, well, it's the same thing. We're having this mesh, so there it's a mesh that we created through software from motion types. We're passing the soil there, and we can compute then about volume, height, etc. So really, the types of algorithm, even if it's different technology, can be the same. The real question is what are the precision and resolution, and that is really some hot topic because it depends also of the type of sensors. So we're very used to do that, and we're happy to discuss that after the webinar. And voila. And if you want to go further, and you will have some illustration also later on with the phenobile, but or you're having this depth map, which gives you access to height and biovolume, and I hope I give you some beautiful examples, or you want to know the profile of light interception within your canopy. And so this is some data from Arvalis, where you can look through time at the same canopy at the interception profiles that changes. And that's really important because what you want to know is all my light intercepted by my top leaf layer, or is the light is able to go within the canopy to be intercepted by the leaf inside the canopy. In an agronomical standpoint, more the light is able to go within the canopy, more you are going to have efficiencies, especially efficiencies in nitrogen and water conservation, because you're going to have more surface, more materials that are green, and probably a reduction of VPD, vapor pressure deficit, so things for water stress estimations. And this is really, really valuable. So those are the types of things we can do with LiDARs, and we do routinely with our customers. Finally, we do compare, and we did publish on that different technologies. So we published a paper in Frontiers in 10 Science where we compare height estimation using LiDARs or SFM and drones. And it's not easy to compare and to evaluate which is the most accurate, because we know manual measurements are extremely inaccurate as well. So there's a whole paper describing that. To make short, the key home message, the takeaway home message, is we use repetition between exactly similar modality to be able to evaluate which of the two technologies is the most repeatable. And what we've shown is that LiDAR technologies are way more repeatable than software from motion. This being said, software from motion is often more accurate than manual measurement. So please have a check to this paper and look a little bit how you can try to do to address traits you're able to assess from 3D sensors. Okay, another use case that we're going to explore with Jeremy now.
So yeah, so we talked a lot about traits that we can directly retrieve from 3D information, but sometimes you want to use a combination of different sensors. So in this example, a 3D RGB camera and 3D sensors to have a really accurate, more complex traits, and in this case, the width ear density. So back to the basics. What is density? It's a number, so the ear density, it's a number of ears divided by the surface. So it's what we will call a footprint. So for example, in those two images, so we are in a breeding trial, and even if the measurement heads that held the sensors are not moving too much, the difference modality, the different microplots of which are different heights. So, for example, on this one, the footprint of your image is way lower than for this little microplots where the footprint is higher. So you definitely need to take this into account just by construction of your trail to have an accurate ear density. And I will just describe in few words just afterwards how you can do this, either by combining RGB camera and LiDAR or two RGB camera. So that's those methodologies are developed at Hiphen, but they are also developed in the CAPT team that we are part of, and especially with the two RGB camera methodology. It has been done by our partner from Arvalis. So, how to compute width head density accurately with an RGB camera and a LiDAR? So, from the RGB camera, it's simple. You use artificial intelligence, and so it's not so simple, but it's not the topic today. So we use artificial intelligence to retrieve the number of widths here within the image. So we are able to counting the number of width heads. Then with the LiDAR, that is laying just side by side with the RGB camera, we are able to generate 3D point clouds of our width canopy. So we are able to compute the height and the evolution of the height, if needed, along the microplots. So for each image, we have the exact distance between our LiDAR and the top of the canopy, so between the RGB camera and the canopy. So because we know accurately our camera, we know the field of view as well. We are able to compute accurate footprints of our image. So now we can just combine the two, and we know that we have a certain number of width heads on a specific surface, so we can compute the width head density. And so even if you have microplots of different heights, or if your measurement head is moving because you are doing the thing in the field, so the things are not perfect, we will take this into account with this methodology. Now we can do quite the same with another technology. So with the stereo vision with two RGB camera. So the two RGB camera need to be well calibrated, and then you will have two images from the same scene. So it's what I started to explain in the last slides. It's you will need to match the two images. And by matching those two images, you will have a disparity map. And the disparity map is directly linked to the distance between your canopy and your camera. So basically here you are seeing a depth map. So you are able, same as previously, the number of width ears by artificial intelligence within your image. And then you want to count your width ears in a specific part of your image. So here it's I think it's a square of 50 by 50 centimeters. And so all of this, so you can extract all the part of the image that is part of this plan of 50 centimeters. And then inside this mask area, you are able to have the number of width ears, and by dividing the two, you will have an accurate width head density trait.
Yeah, so today we're trying to evaluate at CAPT what are the most efficient method between the two we showed you. But I think it's really important, and I'm really happy we showed you those examples to show you that there's many ways to assess the same problem that are going to have different resolution and that are going to be taken into account for different reasons. So we're closing on to the end of this webinar. So just in order to be a little bit salesy and to tell you, okay, we use all this technology we showed you routinely at Hiphen. So if you want to have more information about them, don't hesitate to reach out to us. I'm going to illustrate you that a little bit. So we use them. We have three main products, which we call Phenoscale, that is phenotyping for drones, a platform to allow you to process your drone data in a really scalable way. Phenobile, which is the automated robot I will illustrate to you, and Phenostation, where we work on vertical farmings and also for scientists in greenhouses and a little bit on fruits. Regarding Phenoscale, well, we use the 3D systems really through structure from motion. We're able to extract a lot of features from there. And if you want to be able to scale your operations on drones, have information like lodging, heights, etc., please don't hesitate to reach out to us. Regarding Phenobile, so today you're having quite a number of the systems that are around us today, phenotyping wheat, maize, but also some more exotic crops such as sorghum, lentils, etc. They are in Germany, France, Morocco. So we use them especially for the LiDAR in the field, and they give us a lot of very valuable information also for water deficiencies evaluations. Finally, the phenostation. So the phenostation, here is the example of what we did with INRAD Nancy, where we installed and phenotype trees that are in pots in order to assess how they will be doing once they go into the forest. We were also working on with other types of fields as vertical farmings, and we use time-of-flight cameras, LiDARs, and a little bit also of stereo vision there. And we'll be more than excited to show you more use cases and discuss more about your need you would have for Phenostation. Whatever is your topic, we're always happy to discuss with you.